Welcome back to How to Program. A warning that this show is best viewed in order. And if you have not seen our previous episodes, I invite you to click below to go back to the first episode and catch up from there. The show is sort of designed around the idea that we do things, kind of in a progression. And so if you haven't seen the previous episodes, you might get lost. So the best way is to just start with episode 1 and keep going. This is episode 10, binary, and this is going to be our last episode on binary before we dive into real programming, so you should be really excited if you've been following along. And we're going to talk about how to store text in binary. So first of all, a character, just as a reminder, is a single symbol used in writing. For example, the letter A, the period symbol to end a sentence, the capital letter A, the space, etc., like representing a space would be a character. And a series of characters next to each other, we call that a string in programming. Because, it's just one character after the other. We say it's a string of them, a series of them. A string includes all the characters in a given phrase, including potentially spaces, punctuation, like period, exclamation point, that would be punctuation. Going to the next line, if you were to go to the next line, or any other symbols that may be needed to represent that piece of text. Now, how can we represent text as numbers? Because as we just saw, binary can represent numbers very well, but how do we represent text? Well, there really isn't a way apart from just assigning arbitrary numbers and saying that that number means a certain character. This creates a table, of mapping like a certain number to its symbol. And we call this table, we call this a character map or a character table. Or more commonly, we call this a character set. And a character set is like just literally this assignment of numbers to symbols. And it's just completely arbitrary. The numbers don't mean anything. It's just this number means this symbol. Someone decided that, and now we use it that way. Now, because of the way coding or programming evolved, things being developed mostly in the Western world first and largely in America. Initially the character sets that were the most common were the ones that were used for the English language and could only represent the, basic English alphabet. So over time, of course, new countries starting to also write software and also start writing programs that people needed to use in their own languages. So new character sets started to be introduced to be able to support languages that were not just English, like other alphabets, other symbols, like European languages that have these accents, all kinds of different accents. Asiatic languages, like languages from Asia that have their own set of symbols, like Japanese or Chinese or Korean, and eventually this expanded to include all potential languages in the world, even ones that are not very frequently spoken, but that are still spoken or written or used in certain parts of the world. Certain companies created their own proprietary means it's owned by the company, like property, it's the same word as the same root as property. So they created their own proprietary character sets for their own software. For example, Windows has a bunch of different character sets that you can use that are only really work with Microsoft and Windows products, honestly. The first character set we're going to look at is also the most commonly used, and it's called ASCII. I say ASCII. I think most people pronounce it that way these days. And it stands for American Standard Code for Information Interchange. Now, you don't need to necessarily remember that, but it's good to at least see it once and know what it means, right? So ASCII uses 128 numbers, which very conveniently fits in 7 bits, to represent 128 basic characters with numbers ranging from 0 to 127. So some of these characters are not like letters or spaces or anything like that. They're like special codes, like the tab character, like when you want to tab over, like add a bunch of space before a paragraph. Or this line feed character, which used to tell the printer to just go to the next line, So now, printers don't quite work that way necessarily, but the names have remained. So some of these names may look a little bit odd, and that's because they came from a different time, when computers didn't necessarily work quite the way they work now. So this is a table of the decimal and hexadecimal number representations for particular characters. The table on the left is mostly what are called control characters. They tell the computer to do something. They don't necessarily. They don't have a visual representation. Most of them don't, and some of them are just no longer used. Like device control 1. Like I don't think anyone really uses that right now for anything meaningful, at least. And then you get into starting at about decimal 32. You start to get into characters that we actually as human can understand, for example, the space character, the exclamation point, the number digits. And you'll notice a very important thing. The number digits don't correspond to the binary number representation. Like the digit 0 in ASCII is 49 in decimal. It's not 48 in decimal. It's not 0 in decimal, right? So the numbers don't match up with their binary representation when it's represented as a string in this character set, in this ASCII character set, where we arbitrarily map these symbols to particular numbers. Another important thing to look at is that the lowercase letters and the uppercase letters have different numbers for them. Well, that's because they're different symbols. So of course we couldn't represent an uppercase A with the same number as we represent a lowercase a, which also means that when you're comparing characters, uppercase and lowercase are different. And this is important. We'll see this later, but it's just important to remember, like, uppercase and lowercase are represented in binary. They're represented as different numbers, so they don't equal each other. There's some limitations to ASCII, which are pretty big. For example, well, I might have said this, but ASCII cannot represent other languages than English, and this is a big problem. So anytime you're storing user input, like this is a real user who's entering some data, you should not be using ASCII. You should be using another character set. We're going to see one which is probably the most commonly used at this point, that supports other languages than English. Because if you don't, then anything that the user enters in their own native language is just going to look weird, because it's going to be, it's going to be trying to use that number from that other character set, and it's going to translate differently in ASCII, in binary. You know what I mean? You can imagine how this would be different, right? So ASCII, however, is widely used when storing the text of programming code itself, because most languages frown upon you including other character sets than ASCII in the code. In the code itself, like in the code that you're writing, most of the time you're expected to only be using the English characters, because we don't want anything fancy or anything complicated to deal with when we're dealing with, like translating this code basically into the machine language that the processor uses. Now, communication of text information between computers, that can be safely done via ASCII, as long as no user text is being transmitted, which would require the other character set to be used, of course. So if you're translating information that only computers understand, that contains no user information, that has any chance of being in another human language than English, then fine, you can use ASCII. Otherwise, you're probably better off not using it. So the other big character set that's being used these days is UTF-8. UTF, it stands for Unicode Transformation Format version 8. It was originally proposed in 93 and formalized in 2003, so it took 10 years to really get it to be fully accepted. And since then, it's been growing widely in usage and is by far the most commonly used character set these days for representing data of all languages. Unicode is a term that it refers to an industry standard. This is like people get together and they agree on how things are to be, which is called a standard, right? Industry, because it belongs to, it's a bunch of people who work at different tech companies that write software that get together and decide on these standards. And this is a standard that is decided for the consistent representation and handling of text expressed in most of the world's writing systems. So this can cover things like, Korean or Japanese, all different types of symbols in Japanese, because Japanese has more than one set of symbols. Chinese, it can basically do all kinds of languages. It can do the Arabic languages, that have very interesting characters, it can do it all. So UTF-8 itself is divided into what are called planes. And planes are just sets of characters, they're just logical sets of characters. Now, each plane contains about 65,500 characters, and there are 17 planes total. The first one is called the basic multilingual plane, and this is basically the letters or the symbols that are going to be used in the most common languages of Earth. And you'll see why this is the basic plane and the first plane in a second, and I'll explain why. But it is the most common characters that people are going to use. By and large, you know what I mean? Like the majority of Earth is going to be able to express themselves within those 65,536 first characters. But beyond that, there's 16 additional planes, which represent literally every possible writing system in the world that is in use. You know what I mean? That someone would actually like use in a computer, I think is the way to think about it. So that makes a grand total of over 1 million characters. So just think about that as 1 million different possible symbols that you can represent with this character set. So it's huge. You're very, very unlikely to not be able to represent what you want with this character set. Now, one of the beauties and really the clever bit of design in designing UTF-8 is that it uses a variable number of bytes. Sets of 8 bits to represent characters. A single character, so again, think a character here in this case is a symbol. So one symbol has a code, right? And we call that code a Unicode code point because Unicode is this agreed upon standard, and they define like what numbers map to what character in all these different languages, right? So each individual character has a code, and that code is called a Unicode code, and when you put them together, they make it what's called a Unicode code point, which is the character, like the symbol, plus the number that represents it. Now, that character can be represented with from 1 to 4 bytes, depending on which character it is. Now, the first 127 characters of UTF-8 are the same as ASCII in binary representation. This is by design, so that any text that is represented in ASCII, in the character set of ASCII, automatically is also UTF-8, because both sets of characters overlap for the first 127 that compose ASCII. So this requires no conversion. So if you have ASCII text and you want to display it, in UTF-8 format, no conversion is required. This is a pretty big deal because it makes a lot of things just automatically work that otherwise wouldn't work and would require conversion and be problematic. After that, when you go past those first 127 characters, you get more than 1 byte being used to represent the characters. And the number of bytes vary depending on which character is used. So the further you go, and we talked about these 17 different planes full of different symbols that you can represent, and they each have a number. So the further up the numbers you go, which is going to be rarer and rarer symbols, like less and less used symbols, the more space you need to represent it. And if you think about it, this is pretty smart because the characters that are the most common in humanity, which are going to be sent over the network on the internet all the time, the most, are the ones that take the least amount of space to represent. And this is the beauty of this. This is like the genius in this design, is that the most common characters are the ones that take the less space to represent. This is why this character set became the most used, because it's also the one that takes the least amount of space on average. Now, UTF-8 characters or Unicode characters are sometimes written in a weird way. They're written like U plus 20 AC or U/20 AC. U plus or U slash means this is a Unicode code point. And the 4 digits after that are the hexadecimal representation of the Unicode code point for the character, where each hexadecimal digit represents the value of a single byte for that number. Now, I want to make a big important note here. This number is the number of the Unicode code point. That's the character and the number. That's what that number represents. It does not automatically translate into binary into UTF-8. So don't go try and take this hexadecimal number and put it in binary and try to hope to get the same thing. It doesn't quite work that way because of how UTF-8 has to deal with the fact that it has variable amounts of bytes that it stores data in. So let's look at how UTF-8 represents, its Unicode code points in more than one byte. Well, it uses this kind of scheme. If you stared at it long enough, you would kind of see how it works. Basically, it uses the first byte, the first bits of the first byte, the leftmost bits of the first byte, I should say, to basically, point out whether 1 byte is being used, 2 bytes, 3 bytes, or 4 bytes are being used. And you can see this kind of clearly, in this binary UTF-8 column here. When there's only 1 byte being used, the first bit, the leftmost bit, is 0. When there's 2 bytes being used, it begins with 110, and then the other digits are part of the code point. And then in the second byte, it starts with 10, and then the digits are part of the rest of the digits are part of the code point. It does the same thing for 3 and 4 bytes, where it uses more ones on the leftmost byte on its left bits to basically show off how many bytes it's using. So as you can see, as you go further up the code points into higher and higher ranges that are less and less used, you end up using more and more bytes to represent the data. And so that's just how it works, without getting into too much of the details, which you really don't need to know unless you are going to try to write something that could print out the characters manually or something. Most of this is taken care of for you, but it's just good to know how this works. Okay, so next lesson we're going to start coding, and we're going to first explain what higher level languages are. A language, is just a way of writing code. It's just like a language like English or French is a way to talk and express opinions and ideas. A language in software is also a way to tell the computer what we want to do, and there's different languages that let us do this. And we'll kind of talk about their differences and why you might want to pick one language over another, and what language is a good language for me, and all those questions that come up quite often. So that'll be the next episode, and I hope to see you then. And you can also like our Facebook page to get updates as soon as the episodes come out, and I really recommend you do that. And if you really like our channel, you can also like the video, comment, and subscribe, and let us know that you like it. All right, we'll see you next time.